In this video, we're going to be talking about proof by contradiction. So another one of our proof method strategies in this chapter. So in my mind, there's really two types of proof by contradiction. We'll do first type first and go from there. So to prove some proposition P, really think of a statement. The approach is we're going to assume not P, and then come to some contradicting fact. It could be something that directly contradicts something we said here in these kind of like dots, or it could just be a basic fact like 1 is less than 0. And from that contradicting fact, we'll conclude that it was wrong of us to assume not P, and that therefore P is true. Here's an analogy, or basically not an analogy, it's a proof by contradiction. So sorry for any spoilers out there, but let's say the goal is to prove that Santa Claus is not real. And so the approach I would take would be a proof by contradiction. We're going to assume the opposite. So if this is our P, that he isn't, so we're going to assume that he is real. So assume not P. Okay, assume he is real, and then according to the legend, if he is real, then that implies that reindeer can fly. But that's already our contradicting fact. This isn't possible. Reindeer do not in fact fly, so they don't fly. Therefore, we were wrong to assume not P. And what is indeed true is the original proposition P up here. Therefore, Santa Claus isn't real. So that's really what proof by contradiction is. We say, okay, here's your statement. I claim he isn't real. And the best way I could do that is say, well, assume that he is. Saying the opposite leads us to some contradiction. So in fact, we were wrong to assume the not P, and that in fact, the original proposition P was true. It seems like a backwards argument, but we do it all the time in day-to-day life. All right, let's do an example with some more math-related terms. So before that, we need definition 3.58 from the book, which is a rational and irrational number. So a rational number as P over Q, where P and Q are integers. And the denominator can't be 0. And then an irrational number is a real number that is not rational. Your book does a classic proof of proving that square root 2 is irrational. They present two proofs, so I'm not going to do that one again. I'll do a different problem involving rational and irrational numbers. So the example I'll do is prove the sum of a rational number and an irrational number is irrational. And just as a side note, as always, we should try to just do a reality check. So I'll think of a rational number. Let's say that's 1/2, and then I take pi, an irrational number. There's really no way to combine this with just pure math expressions. What most people would do would say, okay, well, this is 3.14, and then I could add 0.5 to it, which would be 3.64, but that is 3.14 is not pi exactly. You basically have truncated this irrational number into a rational and then gone from there. But as you know from math, you wouldn't be able to combine these two terms. You would just have to write your final answer like that. So it seems like it's a true statement that a rational number plus an irrational number is irrational. But let's prove it for any two rational and irrational number pairs. So here's the proof. And notice that there is no if-then statements in this proposition or problem here. It's really just, there's your proposition P. The sum of a rational number and an irrational number is irrational. So there's really not an if-then, if P then Q. So that's one way I recognize that maybe a proof by contradiction is best, because proof by contradiction, one of the ways of doing it is just you see a proposition P that you need to prove. And there's no if P then Q statement. So that's one way to recognize them. So here we go. I'm going to say let x and y be rational number and irrational number respectively. And I'm going to do proof by contradiction, so I should always label that in my proof. So I'm going to say assume not P, which really means assume that x plus y, the rational and irrational number, is a rational number. Remember, P, that blue statement, is the sum of a rational number and an irrational is irrational. So not P would say that this has to switch to rational. Since x is rational, x can be written as a over b, b not equal 0, a and b are integers. By the definition of a rational number. So then we have x plus y equals a over b plus y. And we assumed that this sum is equal to a rational number. And so I'll just say c over d, d not equal to 0, c and d are integers. So just to recap, we have x. We assumed this was a rational number. Then we said, and we assumed that this was an irrational number. So there's really no way of writing it as a fraction. And then we assume that the sum is rational, meaning the sum here, x plus y, reads to a rational number. So that's our setup so far. And I want to come to a contradiction. Well, I have this equation really, a over b plus y equals c over d. And I know where I'm going, but if you didn't know where to go, you would just say, okay, well, let's solve for y maybe and see where that leads us to. So this implies that y equals c over d minus a over b, which equals, if you just do a common multiple on the bottom, common denominator, that would be bc minus ad over bd. But that seems a little strange since we said up here that y was irrational, but now we're getting y is equal to some fraction. And in fact, you could say, well, this is y equals, I'm running out of letters here, but we'll say maybe dw and z, where w equals bc minus ad, bd, and z equals bd. And furthermore, we know that bd does not equal 0 since b does not equal 0 and d does not equal 0. And hopefully you see now that y under these implications, these kind of following steps, y is equal to two integers being divided. And the bottom's not 0, which means y is a rational number by definition. But what did we say earlier in the proof? We said that y was irrational. So this is our contradicting fact. So this is a contradiction. We stated earlier that y was irrational. And this really is the end of our proof by contradiction, but let's just remind ourselves what our goal was after all. We were wrong to assume not P. So P, which was P, the sum of a rational number and an irrational number, is irrational. Must be true. And that's the end of our proof. So again, proof by contradiction is a little like proof by contraposition. It seems like we're going backwards and then going forwards. So I really recommend you look over this problem again, try to recreate it from scratch on your own. Look at our solution here in case you get lost, and then make sure not only do you understand all these little details in between of defining the definition and the variables, but also the underlying arc and concept that we're trying to use to prove by contradiction. We're going to do one more proof by contradiction. I think it falls into a second category of proof by contradiction, but I'll explain what I mean. So we just saw, right, P, our goal was P. We assume not P, contradiction, and then conclusion P, where P was just like a proposition statement. It wasn't an if P then Q. So I want to go over the case where you have a if P then Q. So we have a if P then Q. You have two ways of really proving this. You can either go by contraposition, which you're doing not Q, not P, or you could go contradiction. Slightly different, but necessary to flesh out the details of what it means. So if we're going to go by contradiction with a if P then Q, you're going to say, we're going to assume this is false, the implication. That means the negation of this implication is true. And then the negation of an implication we saw in the previous video is logically equivalent to the P and not Q. So that means P and not Q is true. And so what we're going to do in a proof by contradiction is we're going to assume this. Hopefully it leads to a contradiction. And then we, in some sense, kind of go backwards up to P then Q, which means if P then Q is true. So it has that same going, assuming the opposite, getting to contradiction, then going back to the very top. It's just a little different because we have the if P then Q structure instead of just the proposition P. So let's see an example. So this example out of the book, but basically says if A if A is less than B plus epsilon for all epsilon greater than 0, that means A is less than or equal to B. So the book has a if P then Q. Basically, we want to show or prove that this is true. And in the spirit of this section, we're going to do a proof by contradiction. So we assume false. We assume if P then Q is false. Like I said up before, that implies that if P then Q, then the negation is true. And that's logically equivalent to saying P and not Q is true. So that's going to be our basis here, where we're going to jump off from. So assume P and not Q. That is, assume that that A is less than B plus epsilon for all epsilon greater than 0. I'm going to call this equation or inequality number 1 or statement number 1. And we also are going to assume, so this is P, and we're going to also assume not Q, which is that A is greater than B. And we're going to call this inequality number 2. Okay, inequality 2 has A greater than B, and that implies A minus B is greater than 0, just by subtracting B from both sides. and that implies a minus b divided by 2 is greater than 0, just dividing each side by 2. So keep that in mind. By 1, inequality 1, we have a is less than b plus epsilon for all epsilon greater than 0. Notice that a minus b over 2 is greater than 0, so that could be our epsilon. So since a minus b divided by 2 is greater than 0, let epsilon equal a minus b over 2. And inequality 1 becomes, so I'm just going to take this epsilon here, plug it into there, and rewrite this expression. A is less than b plus a minus b over 2. And we're just doing a little algebra here. Means a is less than 2b plus a minus b all over 2. Just putting the b over 2. That means a is less than b plus a divided by 2. Again, some more algebra, you can verify it all. A is less than b over 2 plus a over 2, which means a over 2 is less than b over 2, subtracting a over 2 from each side. And finally, we have a is less than b. I'll put a star here. But if you recall, in the very beginning of this proof, we assumed P and not Q. In particular, we have this not Q, A is greater than B. So this star contradicts that. But star, which says A is less than B, contradicts 2, which said A is greater than B. So that means we've arrived at a contradiction, which is really the goal of proof by contradiction. And just recapping it all, assuming if P then Q is false, led to P and not Q is true, which led to